In this lecture segment and the next, we'll look more closely at the grid display class. As we saw earlier, grid display generates the text grid display of the simulated world. And we talked about grid display's use of displayables in the prior segment. Now let's go through the details of the grid display class. First off, note that grid display implements display, not to be confused with displayable. And as you can see in display.java, this interface defines just two methods: add displayable and update. The first adds a displayable to the list of things to be displayed, and the second causes an update to the display, for instance, a reprint of the grid. And of course, grid display implements both of these methods. There is add displayable and update. Now, like most interfaces, display represents an essential behavior, in this case that of being a display. A display must be told what to display, add displayable, and when to update the display, update. Anything else is implementation detail. The particulars of how displayables are tracked, is it a linked list or an array, of how they're displayed, a text grid, a graphical GUI, those are not of interest to the code that is calling the methods of the display, so those and any other details are left out of the interface. And once you have a hammer, everything looks like a nail, and interfaces are a really big hammer. One of the most common elements of OO design is the process of distilling the essence of some behavior, like displaying, into an interface, and then implementing the interface with one or more classes. The point, as we've emphasized before, is to let different implementations of the behavior share a common interface type, and thus be used interchangeably. And as we'll see in a bit, there are actually two code worlds classes that implement display. The second, dump display, does a debugging printout of the world. Its update works completely differently from that of grid display, but it still behaves as a display. Note also the use either in dump display, right here, or in grid display, up here, the use of a list of displayable reference for the DSP's list of displayables, which is a linked list. Can a list reference point to a linked list? Well, sure. Unsurprisingly, list is yet another interface. It's declared as part of the Java collections, and linked list implements it. So linked list is a list, and a list reference can point to a linked list or any other class that implements list. List describes the essence, if you will, of listness, the methods essential to working with a set of objects that fall in an indexed order. Question 1. Go look up JavaOO list in the Java docs and find out how many classes implement it. Are there any that you recognize? And about how many methods do those classes have in common? And returning from a pause there, here is the Java docs in question, and you can see that among the classes implementing list are array list, which we're familiar with, and linked list, and apparently a number of others as well. And they share in common approximately 25 methods, all those of the interface list, which all have to deal with managing an ordered list of objects. Note, by the way, that you can type qualify interfaces that use generics like list, and as we did here in the grid display code, list of displayable. Now, that's just the same as when you're qualifying a class. There's only one list interface, but you may add a type qualifier to specify that only objects of that type may be added to the object pointed to by that reference. And other possible examples might be, list of animal, which would be a list pointing only to animals, or a list of string, or what have you. Now, it's usually better to use interface references rather than class references to point to objects if the class implements an interface. For instance, because DSPs is declared as list, a general purpose interface, rather than as linked list, a specific class, then we can change the type of list that DSPs points to later on, say to array list like this, and we won't have to change the reference type, either here or down in the code. We'll only need to alter the new operation that creates the actual object. Now, grid display has a nested class, params, right up here, that has members representing basic parameters of the display, including things like the number of rows and columns, and the grid step, which says how many x and y values each row represents, and how many y values each row represents, and how many x values each column represents. So, for instance, if grid step is 5.0, then animals at row 0 are at y equals 0, those at row 1 are at y equal 5, and so on. Now, params is a pretty simple class. It's just 3 members and a constructor. And in such simple cases, it is sometimes acceptable to make all data members public and to dispense with the usual getters and setters. Such classes are analogous to record or struct variables in languages like C, for instance. And do this only for very simple classes that have no present or anticipated future methods other than a constructor. Now, method update down here, moving on to another topic, sets up a 2D array of strings, and it uses row and col down here to index that array, for instance in the for loops right here. Now, these are not ints. They're integers. You may already be familiar with Java's elemental wrapper classes, but even so, they're worth a discussion from the standpoint of object-oriented design. Java variables fall into 2 major categories: references and elemental types, like int or char, boolean, double. Elemental types, like int, are not references, nor are they dynamically allocated. Unlike a reference type, say animal, with its allocated target object, an elemental type is just one box containing a simple integer, floating point, char, or boolean value. For each elemental type, Java provides a library wrapper class of similar name but capitalized. For instance, integer or double or char. Objects of these wrapper classes have just one member of the relevant elemental type. And as the diagram shows, for instance, an integer reference, row, would point to an integer object that would have one int member, perhaps containing a 0. You can think of wrapper objects as carriers of elemental values. Now, question 2, go look up the Java docs for java.lang.integer. How do you create an integer object containing, say, 42? And given an integer object, how do you get the integer value, the int value, back out of it? Returning from a pause there, here is the Java docs for integer, and it evidently has a constructor that takes an int value. So we could write something like row equals new integer 42, and get a integer with 42 wrapped in, or integer wrapping up the value 42 inside of it. And then the same docs also show that integer has a method int value that returns the value of this integer as an int. So if we had an int, say x, we could make that equal to row dot int value and get the integer back out of row. Now, the question you may have in mind right now is, why would we wrap a perfectly good elemental integer in this way? Why would we do this? Well, there are two reasons. The most important is that, like every other class, the wrapper classes ultimately derive from object. So, for instance, an integer is an object. Collections like ArrayList and LinkedList cannot contain elemental types. They are collections of object references. Even if you type qualify them, the type must be an object subclass. So you cannot, for instance, say LinkedList of int. Collections rely on the fact that object is a universal reference that can point to any object that might be added to them. But as we say, elemental types are not objects. So to put them into a collection, you need a go-between class that wraps the elemental into an object. We can't have a list of int or a linked list of int, but we can have a list or linked list of integer. And if you want a collection of some elemental type, you have to add wrappers to the collection, not elemental values. The second and lesser reason for wrapper classes is that an integer reference can be null. It's sometimes convenient to have a way to say there is no valid integer value here. You can't assign null or another non-int value into an int. Any value you put into it is a valid integer. But you can set an integer reference to null, thus, and that can indicate that there is no value there at all. And returning to grid display here, row and col are integers, and we might expect to see code then that assigns values into them using the integer constructor, right? And when an int is needed, for instance, for an array index, we might expect to see code that extracts the wrapped int via int value. So maybe we'd have expected to see something like row here in this for loop equals new integer of 0, and then down here when we used row, we would have expected perhaps to see row dot int value to extract the value from the row. Now you can write such code if you like, and prior to Java 1.5 you had to write such code to use the wrapper classes, but that was pretty tedious, and the Java language designers realized that it would be better to automatically do the integer construction in cases where an int was assigned into an integer, and to automatically call int value when an integer was used in cases where an int was actually needed. Thus, you see code in grid display that, like we have here, where we simply assign a 0 into a row, or use row and col integers as though they were ints to index the array grid. And it all works fine. This automatic translation between wrappers and elementals, automatically calling a constructor, automatically calling an int value, is termed autoboxing. Autoboxing was added in Java 1.5 partly in response to the fact that C#, Java's competitor, had autoboxing from its inception. So here's a question for you. Read the code for update, and in particular for compute index, and determine what our reason is for declaring row and col as integers instead of simple ints. Which of those two purposes are we using here? Returning from a pause, well, when a displayable's x or y value is out of range of the grid, then compute index returns a null to indicate this. And we test for a null row or col value before assigning the result of toString into grid. So in this case, we're using wrappers for their nullability. Question 4. There is one case where autoboxing would fail when converting a wrapper into an elemental For instance, grid row call, or if we just did something like assign a row into an elemental integer. In what case would that fail, and what exception results in that case? You can reason it out from what we've said so far, or by trying things out in the sample code, or you can just check online if you like. And the answer is, returning from a pause, well, if the wrapper, say row or call, were null, then it wouldn't be possible to extract an int from them. So a null pointer exception results in such cases. Let's do question 5 now. There are many different elemental number types in Java, for instance byte or double or int, and each has a corresponding wrapper class. I'd like to declare a type qualified list, linked list let's say. So looking at something like linked list of some type in here, and I want it to be able to contain any numerical wrapper class. So for instance byte, capital B, or double, capital D, integer. It's also okay for it to include objects of the arbitrary precision classes, by the way, big integer and big decimal, but I don't want it to contain general objects like, say, string. So I can't, for instance, get by with a linked list of object. That won't cut it. Now, what type qualifier should I use for this case? And this will require investigating the Java docs for the wrapper classes and any superclasses thereof. Returning from a pause, the wrapper classes all have, the numerical ones anyway, a superclass number. And as you can see, its known subclasses include byte, double, float, integer, and the big decimal, big integer I mentioned as well. It's a superclass then of all the numerical wrappers. So linked list of number could hold any of its subclasses, since integer, double, byte, big decimal, etc. all are a number. But classes like string aren't. Okay, in the next segment, we'll look a little more at the object-oriented design issues related to elemental data, and we'll finish up discussing grid display.